And I'm going to do something real quick and make sure my camera is working. And it's not. Okay, I'm going to shut my camera down and turn it back on. Okay, while we're waiting for that to start, why don't you go ahead and ask your question?
Okay, so is the difference between a propyl substituent group and an isopropyl substituent group just the fact that the propyls are on the ends, the terminal?
Yeah, that's pretty much it.
Okay.
So let's see if I got my camera up and running yet. I've got so much stuff open on my computer. Okay, there's the camera. So let me show you what it is I'm talking about. And I'm going to show it to you in a more than one way. Because some ways it's easier to see than others, but you should know all the different ways I'm about to show you. Okay. I'm going to change my share here. Okay, here we go. So there are these things on organic compounds called substituents. Basically, you find the parent chain and it's something hanging off the parent chain. So let's call this the parent chain. If you have a CH3 hanging off of it like that, that's called a methyl. If you have a CH2, CH3, that's called an ethyl. If you have a CH2, CH2, CH3, that's called a propyl. And I'm going to draw another parent chain here. If you have a CH and a CH3, CH3 like this is called isopropyl. So the difference is for the propyl.
Tony, can you make it a little clearer?
Oh, yeah, it's not in focus, is it?
So it's just because it needs those 3 hydrogens on the ends instead of the 2.
Well, it meets the carbon on the end rather than the carbon in the middle. You see how this is the carbon on the end and this is a carbon in the middle?
Right. If it was in the middle, it would just be a propyl substituent.
No, when it attaches to the middle, it's an isopropyl.
Okay, so the terminal, oh yeah, because the terminal is the propyl.
Yeah, so here the propyl is this. And it's attached to the parent like this. And that's on the end. Mm-hmm. The isopropyl is like this. So can you see how that they're both 3 carbon units, propyl and isopropyl?
Right.
And they both have 7 hydrogens. So they're both C3H7. So that makes them isomers of one another. So if we call this one propyl, a very good name for this one is isopropyl.
Okay.
And there are other ways of drawing these. For instance, if I draw this parent chain again, this is the methyl, that's ethyl, that's propyl, and this would be isopropyl.
Okay.
So you should know both ways. It's more common to know this way than this way. And how do you interpret something like this? Well, the way you interpret this, so I've just redrawn that here.
Mm-hmm.
Every line is a bond.
Right.
And if you don't show what the bond is bonding together, it's bonding together carbon atoms. So these are carbon atoms.
Right. So there's 4 on that one.
Well, and the parent, there's a carbon here, but the substituent is just these 3 carbons.
Okay.
Now the deal is that each carbon also has to have 4 bonds. And if we don't show what the carbon is bonding to, then it's bonding to hydrogen.
Right.
Now hydrogen only makes single bonds, so you have to add, in the case of this top carbon, 3 hydrogens to it so that that carbon has 4 bonds. This carbon has 2 bonds. So I add 2 hydrogens and now it has 4. This carbon has 2 bonds, so I add 2 to it and now it has 4. So with these line drawings, the first thing you need to understand is a line is a bond. Second thing is the line bonds carbon atoms unless the element is shown. And then 3, you add singly bonded hydrogens to each carbon to get 4 bonds to each carbon. So these line drawings are really useful. So for instance, if you have this, which looks like I'm kind of drawing a person almost. Here's their head, here's their neck, and here's their arms. But nonetheless, let's take a look at this. What does each line represent? A bond. So this is a bond. This is a bond. Right next to it is another bond. And we have a 4th bond there. Now, what is this bonding together? And the answer is 2 carbons.
Right.
What is this bonding together? The answer is 2 carbons. But it turns out that the 2 carbons it's bonding together, one of them is also bonded to this carbon on the end. So here we don't add a 4th carbon here. It's just 3 carbons. 1, 2, 3.
Right.
And these 2 bonds, what's at the end of these 2 bonds? Well, not a carbon, it's an oxygen. Okay, so now we have to add hydrogens to this to make it complete. Do you see that this carbon only has 1 bond?
Yeah, it needs 3 hydrogens.
So 3 hydrogens, and there we go. We're in business. Do you see how this carbon has 4 bonds?
Yeah.
No hydrogens.
Mm-hmm.
And this one has 3 bonds, so we add 3 hydrogens, and here's the molecule.
Is that a ketone?
It is. And in fact, this ketone is called propanone. The "one" is because it's a ketone, the "prop" because it has 3 carbons. There's a more common name for this, and you've heard of it, I'm sure. Acetone.
Yeah.
Some people use it for fingernail polish remover. Some people use it as a solvent or whatever it is they might be doing. I use it as a solvent for some paints I use.
Mm-hmm.
But these are 2 names for it. This is the IUPAC name, and this is the common name.
And these are still alkanes, though?
No,
They're not.
They're not alkanes,
They're
they're
not alkanes.
ketones.
So you have to look at the whole thing. There's not like part of it that's an alkane.
You could call this an alkane, but what's the point? I mean, if you're going to call this an alkane, then every
Right.
molecule has alkanes, and it kind of gets boring.
Right, okay.
Alkanes are not a very useful functional group.
They're simple, more so
Yep.
probably than the others.
Yeah, ketones are very simple. And the other thing you need to know about ketones is how to spell them.
Mm,
I know people are used to spelling key with a K-E-Y, but this is K-E.
right.
Okay, so I think I answered your question, I hope, about propyl and isopropyl.
Yeah, you did.
It just depends on where it is attached to that carbon. Okay. You said you only had one question. Issa, do you have any questions?
No, I'm good right now.
Okay, well then I posted a video where we went through a bunch of questions in chapter 23. And rather than start with those, I'm going to start again with these new questions, number 26. And we'll learn about some organic chemistry as we go along. How's that sound?
That's fine.
Are you good with that, Issa? Okay, I'm going to assume that's a yes. This one is actually something that we want to know. This is reactions of alkanes and cycloalkanes. So an alkane is something that has the formula CnH parentheses 2n plus 2. A cycloalkane is something that has the formula CnH2n. So here are some alkanes. This one here is called methane. This one here is called ethane. This one is called propane. And we can do line drawings of propane. Propane looks like this. So just take a moment and see if you can count 3 carbons here and 8 hydrogens. Okay, now to help you out, there's carbon 1, carbon 2, and carbon 3. So 3 carbons. This carbon has 3 hydrogens. This one has 2 and this one has 3. 3, 2, and 3 is 8. This one is called butane, the next one, and it looks like that, C4H10. So this goes all the way to 10, and you should memorize these names and the formulas. So there's butane. These 3 names, methane, ethane, and propane, and butane are 4 names. They don't really match up with anything we know so far, but this one does. 5 carbons, pent, like a pentagon. 6 carbons, hex. 7, heptane. You guys remember those prefixes we used for diatomic molecular compounds?
Yeah.
Yeah.
These are
Monodiac.
pretty much the same at the beginning, like instead of hepta, it's heptane. Instead of octa, it's octane. Nonane and decane. And when you make the line drawing of these, this is what they look like. The pentane is the bird. I always like drawing pentane because I can say, well, Yeah, I gave all my students the bird in class.
That's rude.
No, it's not. It's pentane.
Just kidding.
It's only rude if you think it's rude, but not the way I meant it.
Hmm.
I see. I get to say I gave you the bird, but it was not the bird that most people think.
Hmm.
It was the chemistry bird.
Hmm.
All right. Now, why don't we have the line drawing for ethane? Well, because that's the line drawing for ethane. What might you mistake that for? An underline or a dash? So let's tilt it a little bit. Is there anything you might mistake that for? Maybe a backslash,
Hmm.
forward slash, or maybe you say it looks like that, and then now you think it's an L or an I, right? So drawing a line drawing for ethane is not easy to do. And methane, you could try to do that for methane because you can't show a carbon-carbon bond. So just a single dot. What might you confuse that for?
Period.
It looks like a period to me. So these guys have their line drawings. But when we talk about alkanes, these are all straight chain alkanes right here.
Mhm.
But if we look at this guy here, this is also C4H10. 1, 2, 3, 4 carbons, right? 3 hydrogens, 3 hydrogens, 3 hydrogens for 9, and one more in the middle for 10. Okay, so this formula is for straight chain alkanes and for these that are called branched. Now, cycloalkanes, this is your simplest one, and it's called cyclopropane. So why is it called cyclo? And the answer is because the carbons are all connected back to one another. And why is it propane? Well, propane, 3 carbons. What do you think the name of that guy would be?
Cyclobutane.
That's right, cyclobutane. And how about this guy? I call it the house.
Was cyclopentane.
Cyclopentane. And how about this guy? The house with a little hole in the floor.
Cyclohexane.
Cyclohexane. And you can even draw 7. 7 would be a house like that. I think I said hexane, but cycloheptane. So here's 7. And 8 would look like a stop sign. You guys know what stop signs look like? You're supposed to say, of course we do. And we stop at them. Cyclooctane. Okay.
Hmm.
So just a quick review of these guys, not review, but preview, if you will. And let's look at reactions of alkanes and cycloalkanes. So what happens with alkanes is you have CN H2N plus 2, and you react it with oxygen, you're going to get CO2 and H2O. So that's the reaction with oxygen. It's an oxidation reduction reaction, so it's a redox reaction. And specifically, it's a type of redox that's called combustion. So you guys have heard of this reaction before, right? So this is combustion. And then there's another one called halogenation. So we take a CN, H2N plus 2, and we react it with a halogen like chlorine. Or it could be bromine, or it could be iodine, or it could be fluorine. But a halogen, you're going to get CN, H2N plus 1. So one of the hydrogens is gone. And what is in place of it is one of these halogens. So where is the hydrogen here? Well, it combines with the other halogen and makes an acid. So this is called halogenation. And so you might ask, well, where does the chlorine go if there's a bunch of hydrogens? And the answer is anywhere it darn well pleases. So for instance, if I have CH3, CH2, CH3, and we add chlorine, the chlorine could add to this first carbon, and we could have CH2Cl. Or it could add to the second carbon. Or it could add to the third carbon, which is the same as this. Now, here's another way to draw this. So this is a Lewis structure. So I could draw it this way. We get this. It doesn't matter where I put the chlorine. I could put it here, here, or here. It doesn't matter. So these two are the same. And I could also draw it this way for the other product. Where these two are the same. So which one was faster to draw, the top one or the bottom one?
Top.
Top one. Now, there's another way we can draw this reaction, and it looks like this. There is your propane. Now, you'll notice I didn't write plus HCl, but I'll go ahead and write that. So here's one, and there's the other. So which of these three ways of writing it is the fastest?
The line drawing?
The line drawings. They're so much faster. Okay. So that's a halogenation. You can replace any one of those hydrogens. Now notice when I write this out and I have one of these plus one of these, and then I write two products, the reaction isn't balanced. The purpose of writing out an organic reaction is usually to show you all of the possible products, not a balanced reaction. Again, when you're showing the products of an organic reaction, you're usually trying to show people all of the possible products and not a balanced reaction. So let me show you the real reaction that would happen here. So I'm going to show you with A. So what would happen with this is you would get CH3Cl plus HCl.
So is it kind of just acting like an acid base, like with the Bronsted?
Well, no, this is not an acid-base reaction because Bronsted-Lowry acid-base is a what, proton donor and proton acceptor?
Right, but it's still giving the hydrogen one of the chlorines.
But it's not a proton.
Okay.
It's not a proton. So this is really this HCl. There's no proton.
Right.
Okay, now this is also going to react. This is also going to react. So what's happening to this methane is that one by one, the hydrogens are being replaced. So when they say excess chlorine, that means more than enough chlorine for all of the hydrogens to react. So the overall reaction is this. And we're not going to worry about balancing it. So what if I asked you about ethane plus excess chlorine? What would you get? Here's ethane. And the answer is you get CCl3, CCl3 plus HCl. Every one of those hydrogens would be replaced by a chlorine. So if you have 3 hydrogens, you get 3 chlorines, and there you go. So that's the answer to A, reaction of methane with excess chlorine.
And this
Now,
is halogenation?
This is a halogenation.
Okay.
And in fact, it's called a chlorination.
And it's the same process, like regardless of whether it's like methane, ethane, or.
Right. So here, let's take a look now at CH4 plus chlorine. So this is, we're going to adjust A, but we're going to say no excess chlorine. What are your products? And the answer is you'll get all 4 of those. So, you know, if we have a 1-to-1 ratio of these, you got to ask yourself, if you have one of these and one of these, shouldn't we only get that? Doesn't that make sense? You're supposed to say yes.
Yeah.
Okay, and that's true. If we only had one of these and one of these, you'd get one of those. That's for absolute sure. But when we do these reactions, is there really only one of these and only one of these?
No.
The answer is no. There are billions and billions of these and billions and billions of these, right?
Right.
So you could have 500 million react and make 500 million of that. Now this 500 million can react with the other half of the chlorine that hasn't reacted and make that. And let's say half of those react that way. Now you have 250 million of these that could react with still 250 million chlorines that haven't reacted and make that, and so forth and so on. So when you do these reactions, you will actually get all 4 of these. You're going to get mostly this here and less, lesser, and lessest. You guys like that? That's a new word. Mostly, less, lesser, and lessest.
And it's still plus HCl at the end.
Okay, so maybe it's not lessest, maybe it's least.
Mhm.
Okay, but you get all 4. And what's the other product you're going to get?
Hydrochloric acid.
HCl. Is this balanced?
No.
No. Are we showing you all the possible products though?
Yeah.
And that's the purpose here.
So it's saying that it like happens so fast that the CH3Cl is reacting with the Cl2 before it becomes the limiting factor.
Yeah, it's just like, you know, there's so much of these things around that when one of these reacts with one of these, this guy could bump into another unreacted Cl2 and react right away.
Right. Okay.
You know, it's kind of like, you know, I don't know, being in a mosh pit, you get bumped by one person and then you get bumped into another and you don't know what's happening. Okay. Actually, I have no idea what a mosh pit is like, so I've never been in one. Okay. So you can see why they asked this question, the reaction of methane with excess chlorine, because when there's excess chlorine, there can only be one outcome. All the hydrogen's gone. Okay, let's look at the next one. Complete combustion of cyclohexane with excess oxygen. Now for this one, I don't think we want to do any sort of a drawing. We just want to write the balanced reaction. So C6H12 with excess oxygen. So what does that mean about our cyclooctane? Will all of it react or just some of it?
Only some of it?
We have excess oxygen. Will all of this react or some of it?
Some of it?
No, all of it.
Excess
Oh, I mean, all of it. Sorry. Yeah.
O2 is in excess.
Yeah.
So we're going to get only CO2 and H2O.
Mhm.
Let's balance it. How many CO2s? I'd say 6 because we have 6 carbons here and I want 6 there. How many H2Os? Well, I have 12 there and I only have 2. I'm going to put a 6 there. How many oxygens? Well, I have 12 here and 6 here. That's 18. So I'm going to put a 9 here. So this is your balanced reaction for cyclohexane with oxygen to make CO2 and H2O. Oh, and I guess technically for this guy, if we want to make it balanced, we should write 4 here and 2 here. Because they do say balanced. So we might as well make it balanced. So I'm going to go back to A. If we want to make sure it's balanced, we first say methane plus chlorine is going to give us CCl4. We take every hydrogen and replace it with a chlorine. We know the other product is HCl. And so now we balance it. How many carbons here? 1. How many carbons here? 1. That's great. How many hydrogens? 4. How many hydrogens? 1. So I'm going to put a 4 there. 2 chlorines. 4 plus 4 more for 8. So I should actually have a 4 there. And now I can see that I did not balance this correctly. That should be a 4. So there's your balanced reaction for A with excess chlorine. Any questions on number 26? Okay, number 28. What is the structural requirement for an alkene to have cis and trans isomers? So first of all, an alkene is a molecular compound that has a carbon-carbon double bond in it. So this is the simplest alkene right here. And this is also an alkene. You can see the carbon-carbon double bond there. This is called ethene. This is called propene. They both end in ene because they have the carbon-carbon double bond. This starts with eth because it's 2 carbons, which is ethane. This starts with prop because it's got 3 carbons, which is propene. Now, interestingly enough, this you would think would be butene because it's got 4 carbons. And you're really close to being correct. It's actually called 1-butene because there's this, which is also butene, 4 carbons with a double bond in it, but notice the double bond is not on the end. And if we look at the carbons and call this carbon number 1, carbon number 2, carbon number 3 and 4, and over here, carbon 1, 2, 3, and 4, the double bond starts on carbon 2, so this would be 2-butene.
And it's only not in the propene because from the other side, it would also be a 1.
It's the same thing. And as an example of that, this is 1-butene also.
Mm-hmm.
Because we start numbering closest to where the double bond starts, not left to right. Okay, an interesting thing about 2-butene is that this is actually trans 2-butene because there is a cis 2-butene. And cis 2-butene looks like this. So I'm going to draw these out larger. Trans 2-butene. So we have, I'm going to draw them a little bit differently. Here's the double bond. And cis 2-butene. Here's the double bond. And I'm going to draw it this way or this way. Now I'm going to fill out the atoms. So at this point here, do you understand why I drew the carbons where I did?
Right.
Are you good with that, Issa?
Yeah.
Excellent. Now I'm going to fill in hydrogens. Now I want to focus on this part right here. This is a trans. Now, do you guys see why I have the carbons where I have them for this guy?
Yeah.
Now here, instead of writing the hydrogens out, I'm going to put H3 and H3 here instead of drawing them out this way.
Okay.
And I'm going to put the hydrogens like this, and this is a cis. Now, if we look at this guy looks almost exactly the same, except for the hydrogens are down compared to up. Okay, so for a cis trans alkene, you need the following. You need an alkene. Second thing is bonded to the carbons, you need exactly 2 hydrogens. Now, one of the things that you can't tell from the drawings, but it is true, is that the hydrogens have to be each on a different carbon. They can't be on the same one. So here, this one butene does not have a cis trans because there are two hydrogens on one of the carbons, and that can't be a cis trans. So hydrogens on each carbon. And then the way I like to remember it is I draw a line through the double bond, and if the hydrogens are on the same side, it's cis. Same cis. Because they both have that soft S sound, right? And if they're on opposite side, it's trans, like the transcontinental railroad. The transcontinental railroad connected the East Coast to the West Coast, and it went across the country. And it had to cross this middle line, which of course would be the Rocky Mountains. Does this sound like a history class? So of course, the importance of the transcontinental railroad meant that you could get on a train and go across country in a matter of a month or two instead of get in a wagon and make it a year-long journey. And you wouldn't have to get on a boat and sail around the South America to get to San Francisco. It was great. And this is way before the Panama Canal. And another interesting thing is the two sides were being built simultaneously, starting from the East Coast and starting from the West Coast, and they moved to the interior, and they met in a place just north of Salt Lake City. And supposedly the last rail was put in with some golden spikes, but I have the feeling they're not there anymore. Okay. So, are we okay with cis and trans?
Yeah.
Yeah.
Now let's go back to this. What structural requirement is necessary for an alkene to have cis and trans isomers? So we're going to say you have to have a carbon-carbon double bond, but that's redundant because they say an alkene. We have to have a carbon-carbon double bond. We have to have one hydrogen bonded to each carbon of the carbon-carbon double bond. And then we're going to put, if the hydrogens are on the same side, and we're going to show people what that looks like, that's cis. And if they're on opposite sides, they're trans. So what's another way for me to show cis?
Upside down.
Well, how do you know that's not upside down?
It's all your perspective.
It's all in your perspective. See, this one is a cup with water in it, and this one is your cup is empty. I'm kidding. What's another way to show trans? Okay, so it doesn't matter whether it's up or down, just that they're both on the same side. And when we say same side, we mean that if we draw a line parallel through the double bond, splitting that thing into sides. Fair enough?
Yeah.
Yeah. Mhm.
Okay. Can cis-trans isomers exist for an alkane? And B, no. Now, not for an alkane. I'm going to draw something for you that looks like cis. Does that look like cis because both hydrogens are up?
Yeah.
It does, doesn't it?
Mhm.
Now, here's the deal. I'm going to go ahead and put chlorines here. I don't know why, but a lot of people show cis and trans using chlorines. What do we know about rotation around a double bond? Is that possible or easy to do?
No, because of the pi
It
bond.
is not. They cannot rotate around double bonds. What do we know about rotation around a single bond? And the answer is it's really easy. So
Mhm.
this guy can simply rotate, and all of a sudden, it looks like a trans.
So it can happen with alkynes too.
Well, let's take a look at alkynes. And the answer is no, not for an alkyne. Now here is an alkyne. And here I'm going to have to put 2 hydrogens on there, right?
Yeah.
Well, can you rotate about a triple bond? And the answer is no. Triple bonds do not rotate. They do not rotate. However, single bonds do rotate. So I'm going to draw this hydrogen upside down. Okay? And I'm going to draw this one upside down. So normally I draw hydrogens like this. One, I start down, down, across, and I go from right to left. So to draw this hydrogen upside down, I'm going to go up, up, and left to right. So you can see it's upside down, correct?
Okay.
You can see I drew it upside down.
Right.
Can you tell the difference?
No.
No. So there's no cis or trans for alkynes.
And it's really just because you only need the one hydrogen on either end because of the triple bond in between.
It's really because that can rotate.
Yeah.
Wait,
Because-
so is there,
And
or
also-
is there,
Also, if I draw the line through here, you're not going to have 2 hydrogens on the same side or 2 on the opposite side. They're right in the middle of the line. So you could really say for alkynes, it doesn't work because alkynes are linear.
Okay.
so for
So-
alkane for alkane, we said there is no,
There is no cis or trans. And let me see if I can
okay.
show you something. I'm not sure if it's going to work, but I'm going to give it a try. Okay, I've got a video here. Let me see if it works.
So this is a quick demo on how to use the MolView website.
Okay, I don't like
Actually draw
that.
it out. We can put our hydrogens in on it. So we know that the ends of these are carbons. So I can select my hydrogen tool and go ahead and I can draw a bond.
You would think there would be a nice video of this somewhere. Okay, I got to go back to that one site.
So this is a quick
I think they, oh, here we go. Okay, I'm going to do my
structure.
new share.
These types of molecules, it's giving a warning about the 3D structure being inaccurate. I wouldn't worry about that. Just hit OK. If you have questions about that, shoot me an email to make sure that your model is correct. So now we can spin this and we can see it's all single bonds. These dark gray spheres are the carbons. And
So
the
can
white
you see this
spheres are the
ethane here in the
hydrogens.
middle of the
We
screen?
can zoom in on it.
Yeah.
Depending on if you can do a 2-finger zoom with your computer, you can zoom in on it. We can see how everything lines up, and that's the three-dimensional structure. Hexane. Right? So that means that hexane is our base, so we want to have a 6-carbon chain. All right, so that's good to know. That tool
It doesn't actually spin
I'm
it.
going to
Gosh
make
darn it.
another molecule. I'm going to show you a little trick.
So if you can imagine when you're looking at this guy right here, that this little piece with 3 things hanging off of it can actually spin around like a top because you have a single bond there. So that's what's going on there. And you can actually make this molecule and find out that it does spin, right? And if you make an alkene and simply use 2 toothpicks as a double bond and try to spin it, you'll find out it doesn't spin. All right, so back to this. Tony's boring drawings. What is necessary for an alkene to have cis and trans? 2 hydrogens on the double bond, 1 hydrogen on each carbon of the double bond. If the hydrogens are on the same side, it's cis. If they're on opposite side, it's trans. Can cis and trans exist for an alkane? No. For an alkyne? No. How about, can cis trans exist for a cycloalkane? And the answer is yes. So let me show you a cycloalkane that has cis trans. So what did we call this molecule here? Cyclo what? Propane. Now I want to draw it kind of looking at it not as a triangle that's lying flat in the page. So let's pretend this is my triangle, even though it's not a triangle. I want to draw this triangle looking at it from this point of view, from the edge. So do you understand what I'm talking about here? Looking at it from the edge. So this is the way we would draw that. So there's the front edge of the triangle, and it goes back to the point. So this is supposed to give you the idea that you're looking at it from the edge, and here's a carbon, here's a carbon, and here's a carbon. And I'm going to draw that again. Now, if I have 2 hydrogens like this and 2 chlorines like this versus 2 hydrogens like this and 2 chlorines like this, does this give you the sense of hydrogens being on the same side and hydrogens being on opposite sides?
Yeah, one would be
Which one would be the same side version, the left or the right?
left.
And that is cis. And this is trans. Now you might be wondering about the carbon in back. Well, it's got a hydrogen here and a hydrogen here going up and down. So it turns out you can have cis trans for alkenes or cycloalkanes. So if we had a cyclobutane, which looks like this, which would look like this from the edge. So notice on this here that the front edge looks like it's wider than the back edge, but it only looks wider because it's closer to us. And they say that kids who are good at math can't draw. So what would this be?
Cis.
Cis. And what would this be?
Trans.
Trans. And what would this be?
Cis?
It's not cis.
I don't know.
It's not trans. Remember the rules for cis and trans for alkenes?
Yeah, they have to be bonded to different
Hydrogens.
carbons.
The hydrogens have to be on different carbons, right?
Yeah.
Are these hydrogens on different carbons?
No, it's on the same one.
So it's not cis and it's not trans.
Oh, right. Tricky.
Yeah. And in fact, when you think about polarity, this molecule here would be more polar than this one here.
Yeah.
Because these two chlorines, you could definitely say are on the bottom side of that molecule, making it polar. Here, you kind of have to cut it up a little bit weird to make the two chlorines on the same side. And so it would be less polar. Okay. So we finished that problem 28, I think it was. Now it's time to move on to the next problem. So we just did 28. 30. 5 alkenes have the formula C7H14 and a 7-carbon chain. Draw their structures and name them. So for a 7-carbon chain, I like to use a line drawing. One, 2, 3, 4, 5, 6, 7. So I have a 7-carbon chain. Okay, now it says alkene. So in the future, when I draw these, I'm just going to remember 3 mountains. Does that sound right? Okay, so where am I going to put the double bond? I'm going to start here. This one would be called 1-heptene. Now I'm going to draw the next one. And guess what I'm going to do with that double bond? I'm just going to move it to the next 2 carbons. This would be called 2-heptene. But this one has a cis and a trans. Which one is this, cis or trans?
Cis?
It's actually trans because if I put the hydrogen here and the hydrogen here, they're opposite.
Okay.
So I'm now supposed to draw 5 of these guys. So here's my next one I'm going to draw. Is this one. And I'm going to move it one more time. And this is called 3-heptene. And is this one cis or trans?
Trans again then.
Trans. Now, let's draw the cis version of this. Now, for the cis version of this, I want to take this side here and switch it with this hydrogen here, or take this side on the left and switch it with the hydrogen on the left. And it seems to me that the easier thing to do is to take the hydrogen on the left and switch it with that line on the left. So here, can you see the 2 hydrogens are on the same side?
Mm-hmm.
So this is cis 2-heptene. So here, which side am I going to switch? I think I'm going to switch this side, and I'm not going to draw the hydrogens in. I'm just going to do this, and instead of this going up and down, it's going to go down and like that. And this is cis 3-heptene. And these are the 5 7 carbon chains that have an alkene in them. So you might ask, and it's a great question, why can't we just continue along? That is to say, why can't we put the double bond between the 4th and 5th carbon? And we can. So there it's between the 1, 2, 3, 4th carbon and 5th carbon, right? However, this guy is called trans, and that's probably no surprise to you that this is trans,
Right.
but this is called trans 3-heptene. So the way we're numbering this is carbon 1, this is 2, 3, 4, 5, 6, 7, and the double bond starts at carbon 3. So we put down where the double bond starts, not where it ends. And naturally, if it starts here, what carbon does it go to? Well, it goes to carbon 4. If it starts at 1, it goes to carbon 2. So what's the deal here? Well, this is carbon 1, 2, 3, 4, 5, 6, 7. All we've done is we've taken this molecule here and flipped it to get this guy. So they are, in fact, the same molecule. Just like a, check it out. Can you guys see me?
Yeah,
Okay, what's my name?
Tony.
Okay, what's my name?
I don't know. I don't know who you are anymore. Who's it?
What, you don't recognize the bald spot? It's Tony, your old teacher.
I see you now.
Okay, so do you understand that these two are the same thing? It's just one's flipped around.
Yeah.
Okay, so we only do have 5 of these. And these are the 5 right here.
And the same thing goes for the cis2 and cis3, right? It's just those.
Oh yeah, if we were to take this guy and flip it around, oh, excuse me, the cis2, and flip it around, it'd still be the same. So this is also trans. And for this one, we could do the same thing. Okay, so that's the answer to that one. Number 30. Let's go to 32. Now, 32 means I have to teach you how to come up with products where alkenes react and alkynes react. So let's look at reactions for alkenes and alkynes. So an alkene, just to remind you, has a carbon-carbon double bond, and an alkyne, has a triple bond. So if you take an alkene and you react it with oxygen, you're going to get CO2 and H2O. If you take an alkyne and react it with oxygen, you're going to get CO2 and H2O. These are redox reactions, and more specifically, we call them combustion reactions. Now, the next one we call, I'm just going to call an addition reaction. So I'm going to take a very simple alkene, that's the simplest alkene you can have, and I'm going to add to it A, B. So A is an element and B is an element. Or actually, A is half of a molecule and B is the other half. When you do these reactions, this is what you get. I made a mistake, so I have to get rid of this. So notice that you used to have a double bond and now you don't. So you get this, but you also get this. So what does this tell you about A and B? Do they have to go to the same carbon over and over again? And the answer is no. So let me give you an example using a line drawing. Okay, so do you guys see the double bond?
Yeah.
Now in this case, A is hydrogen and B is hydrogen. So this is what you're going to get. The double bond goes away. I add one hydrogen to one carbon where the double bond used to be, another hydrogen to the other carbon where the hydrogen, and I get that. Now let's try something like this. Okay, can you see how I have 4 carbons here?
Yeah.
So I'm going to draw 4 carbons here. But just like above, the double bond goes away.
Mm-hmm.
In this case, A is chlorine and B is what?
Chlorine.
Chlorine. So I'm going to put one chlorine at one end where the double bond used to be and the other chlorine at the other end. Okay, let's try another one now. Only this time we're going to have 5 instead of 4, and I'm going to add H2O. So if I've done this like my other products, here I start with 3 carbons, I end up with 3. Here I start with 4 carbons, I end up with 4. Here I start with 5 carbons. How many carbons do I end up with?
The same amount.
5. Now, I look at the ends where the double bonds used to be, and I need to add stuff there. What am I going to add? Well, to one of them, I add an H, and the other one, I add an OH, because in this case, I can't split up the oxygen and say, well, half of an oxygen goes to each.
Mm-hmm.
So this is what happens.
So
But it
Tony,
turns out there's another product. Does the hydrogen have to go to this second carbon? No, it can go to the third. So what goes to the second carbon if hydrogen goes to the third?
OH.
OH. Only I'm going to draw it this way because it doesn't matter whether you draw it OH or HO, and I just want you to understand that. The important thing is that the line goes to oxygen. Why don't we want the line going to hydrogen? And the answer is simple. If we draw the line to hydrogen, the oxygen can't be bonded to the hydrogen because it's already bonded to something. So we don't want to do this because that doesn't make sense. That would be somehow or other 2 bonds to hydrogen. Nah. So do you understand these addition reactions?
Yeah.
Okay, so here we're asked about draw the structure and give the systematic name for products of the following reactions. Now, whenever they give you something like this and it's not a line drawing, I say go with it. So I'm faithfully reproducing this, except for one thing that I am changing. And the thing that I am changing is I am taking away the double bond, because I know in these reactions, the double bond disappears. Now, that carbon only has 3 bonds. That carbon only has 3 bonds. What do I add to these to make the reaction complete and so that they have 4 bonds each?
Hydrogen on either side.
Yeah, so I'm just going to do it like this because it seems to fit in there pretty nicely. I could have drawn them going up or down or whatever. It doesn't matter. I just put them on those carbons. So that would be the answer to A. Now let's name this. So to name it, you find the longest chain, and that's the parent name. And then you number end to end. So the substituents or branches are on low carbons, like you want them on carbon 1 or 2 or 3 rather than 7 or 8. And then you identify and locate the branches, which are also called substituents. And then you put it all together. Okay, let's find the longest carbon chain. Can you see if I start here at the top and go to here, that's 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's my winner so far. I could start here and go 1, 2, 3. And that's a loser because 5 is greater than 3. Or I could start down here and go 1, 2, 3, 4, 5. So if I start at the bottom, I can get 5. If I start at the top, I can get 5. It doesn't matter where I start. 5 is 5. So I'm going to start here and go 1, 2, 3, 4, 5. So number 1, the longest chain is going to be pentane. And 2, I number end to end. Now, am I going to be okay with this numbering, or do I want to do 1, 2, 3, 4, 5? So you can see I've got the numbering at the top, 1, 2, 3, 4, 5, the numbering at the bottom, 1, 2, 3, 4, 5. One goes left to right and the other goes right to left. And just so that you can distinguish between the two numberings, I'm going to call this one 1, 2, 3, 4, 5 in purple ink. Well, purple ink is no good, I can see now. So I'm going to do green ink.
Well,
1,
To go from
2,
left to right, yeah, because the ethyl would be at the second carbon instead of the methyl being at the first.
well, there's no ethyl. If we go 1, 2, 3, 4, 5, this right here is on carbon 2. But if I go 1, 2, 3, 4, 5, this guy right here is on carbon 4. So do we want this thing, which is not part of the parent, which makes it a substituent or a branch, do we want it to be a 2 or a 4? We want it to be a 2.
How did you know to do the 1 on the upper methyl
Well-
instead of the lower?
Well, we'll see in just a minute, but what I'm going to do here is I'm going to redraw this. Okay, do you agree that this is the same drawing as above?
Mhm.
Okay, I'm going to call this carbon 1, 2, 3, 4, 5. What carbon is this attached to?
2.
Carbon 2. And since it's a 1 carbon unit, we call it 2-methyl. What carbon is this one attached to? 2 or 4?
4. Based on which way that you numbered it.
We want to number it end to end so the substituents are on a low carbon. So do we want this to be on carbon 2, left to right, or carbon 4, right to left?
Carbon 2.
So this is a 2-methyl.
So it's the same.
So we numbered it, and number 3, we find out that we have a 2-methyl regardless of whether we start at the top or the bottom.
Okay.
And then 4, we put it all together, it becomes 2-methyl pentane.
So when we see a CH2, CH3, we're not supposed to think that's an ethyl?
If you do, but not unless it's part of the parent chain. You see, the deal is if I redraw this one more time, and I'm going to draw it a little bit differently. CH3, CH, double bond, CH, CH2, CH3, and then here's H3C. So can you see how these, I made a mistake. Can you see that these two are the same?
Yeah.
The only difference is instead of these hydrogens hanging out, I said, okay, I'm going to put them right next to the carbon. This is the parent. So the first thing you do always is get the parent. And if it's part of the parent, it's not a substituent.
Right, right, okay.
I can redraw this as follows. There's my CH3, right?
Yeah.
There's my CH, right?
Mm-hmm.
There's my CH2, right?
Yep.
And you see that? There's my CH2, right?
Yeah.
And there's my CH3. And then right here, here's my CH3. Can you see that that's the parent?
Yeah, the 5-carbon chain.
And that's a substituent?
Uh-huh.
Now, does this part still look like an ethyl? Well, less so because you can see it's a straight line.
Right.
But here you cannot be fooled by the fact that we have a little bit of a bend. Don't be fooled by that.
Mm-hmm.
Because if we name this guy here, I'm going to show you another molecule. If we name this guy here, group, this is supposed to be CH, a little typo there, a Tony typo.
So
So what's the parent?
octa? Is there 8?
You
Is
think
it-
there's 8 carbons in a row?
Ooh,
Kind of like
It's just
1,
6.
2, 3, 4, 5, 6, 7, 8.
that was my first guess. Maybe I jumped too quick.
No, that's the longest chain. Because if you do 1, 2, 3, 4, 5, 6, and go with hexane, the rule is find the longest chain of carbons. Which is longer, octane or hexane?
Oh. Mhm.
So hexane is wrong. So you see, I fooled you, didn't I?
So there's
Mm.
only 2 methyl groups on that, on 3,
Exactly. And
3,
there's a
6.
methyl on 3
four.
and a methyl on 6. So we call it 3, 6. Well, actually, the long name is 3-methyl, 6-methyl octane. But this would be considered to be wrong because chemists are efficient and we would rather call it 3,6-dimethyl octane instead of methyl-methyl.
Mhm.
So don't be fooled by this kind of garbage. Just find the longest chain.
Okay.
Just start counting all sorts. So you could even call it 7 carbons, right? 1, 2, 3, 4, 5, 6, 7. But 7 loses to 8.
Mm-hmm.
So hopefully I'm showing you things that you get tricked with. Okay, so we've done the answer for A. Let's look at the answer for B. Now for B, what's going to happen here is you're going to get CH3C, double bond, Br, C, Br, CH2, CH3, and you still have a Br2 left over. So you see how I got rid of one of those bonds and added a Br2?
On either side.
Yeah, right here, got rid of one of those bonds and added a Br2. Now what happens is I get rid of the second one. So this is going to be the overall product. It turns out that the Br2, the H2, the HOH, all of these things react with pi bonds. So when we have this, how many pi bonds? 0 pi bonds. When we have this, how many pi bonds? 1 pi bond. And when we have this, how many pi bonds? 2
One.
pi bonds.
Oh, 2 and then the 1.
So these things react with pi bonds, not sigma.
Okay.
So this is a sigma bond. We also have 1 sigma here, and we also have 1 sigma here. So if you have a single bond, it's a sigma. Double bond, it's 1 sigma, 1 pi. Triple bond, it's 1 sigma, 2 pi.
Mm-hmm.
Which one is my favorite? The triple bond, because it's got lots of pi. Okay, stupid joke. Now, how do we name this? Well, what's the longest chain? It's got to be a chain of carbons.
5.
5, so that's pentane. Are we going to number from left to right or right to left? So we just named that. Are we going to number from left to right? 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5?
Left to right.
Left to right, because then we can get the bromines on carbon 2 and 3, right? What do we call that guy? 2-bromo. What do we call that guy?
3 bromo.
Nope, 2-bromo.
Yeah.
What do we call that guy?
Would you still do the 2 dibromo and 3 dibromo?
We'll see. This would be 3-bromo, right?
Uh-huh.
And what would this guy be?
3 bromo.
3-bromo. So the long name would be 2-bromo, 2-bromo, 3-bromo, 3-bromo, pentane. Are chemists going to say bromo 4 times? No. So they will say 2, 2, 3, 3, tetra bromo
Oh, okay.
pentane. So this prefix tells you how many bromines, right?
Yeah.
And then if you have a prefix that says tetra, how many numbers do you need out here?
4.
You need 4. If this said penta, how many numbers would you need?
5. 5.
5. And if it said tri, how many numbers would you need?
3.
And di,
2.
and we don't use the word mono. If there's 1 bromine, we just say 1 bromo or 2 bromo or whatever it is. So this is the name. So we have some very good rules for naming things, so that if you happen to do a reaction and you name something using these rules, and I don't know why, but English is the common language of chemistry. If you name it using these rules, any other chemist in any other country is going to be able to say, oh, I know what that is. Are you with me?
Yeah.
So this systematic name is a worldwide accepted naming for chemical compounds, so that you can write about them and not draw them, and everyone knows what you're talking about.
That's pretty cool.
It's way cool. IUPAC stands for what? International. I don't know what the UP stands for, or the AC. No, wait. International Universal. I don't know what the rest is. Actually, that universal part may be wrong. But it's the, they actually have conventions every year, and they get together, and when they have discrepancies on how to name things, and someone says, oh, by the way, our naming doesn't fit this compound, we need to come up with something. They sit there and they talk about it, and they come up with the rules. And I can't think of a more boring conference than that. Okay. I think, oh, shit, oh, excuse me. That was shoot. It may have sounded like the other thing, but that was actually just shoot.
Oh, yeah.
But I'm kind of, I have an accent, so it may have sounded otherwise. Let's finish with this one because it is getting late, okay? I didn't mean to keep you guys on so long. Okay, the compound 2,3-dibromo 2-methylhexane is formed by addition of Br2 to an alkene. So this is a product. Identify the alkene and write an equation for this reaction. So if this is a product, let's draw the product. So how are you going to draw a hexene? How many carbons is that?
6.
So how many carbons is that?
5.
So I need to put one more line, and now I have a hexane. Where am I going to put my bromines?
On the second and the third from whichever side you choose.
Well, I'm going to, you know, if I get the choice, I'm going to number from left to right because I'm used to that.
Mm-hmm.
Where am I going to put the methyl?
On 2.
So I'm going to put it, there's my methyl. Okay, now over here, I had to have some sort of alkene, right?
So we need a double bond somewhere.
So the deal is we're going to add bromine to this, and so we need a double bond somewhere. So all of this is going to look exactly the same, except what is going to be missing from this if in the product we have added bromine to this? Well, the answer is this has to have the bromines missing.
Mm-hmm.
Where are we going to put the alkene?
From 2 to 3?
Yeah.
Exactly. Boom. And there it is. Can we draw this a little better? Sure. I draw the bromines like that. So here you can see that this has the essence of that. Can you name this guy?
Yeah. It's
You better be able to. It's written right up here, for goodness sakes.
oh, yeah. 2, 3.
Yeah, that's what I was saying.
Can you name this guy?
Yeah, it would just be the 2
It would
methyl.
be 2 hexene. So what's the 2 mean? It's where the double bond starts.
Mm-hmm.
And then it would also be 2 methyl.
And the methyl comes first, even though it's not alphabetical.
Well, you see, when you're talking about numbering where a double bond is, you want that to be part of the parent because the double bond is part of the parent.
Okay.
So that number has to be close to here. In fact, a lot of people prefer that you number it this way. You put that right in front of the ene because that says, hey, the ene starts on carbon 2.
Okay.
So I've seen both ways of numbering these. I think people are switching over to this because frankly, it's better. You could even have something like this, 2 methyl hex 2 ene 4 ine. So hex means 6 carbons, right?
Yeah.
2 means put a methyl here. This 2 means put a double bond there, right? And this 4 means put a triple bond on carbon 4.
Mm-hmm.
Now this looks like a bad drawing because it is. It should look like this. Why is this a bad drawing? Well, that carbon is sp hybridized. That one is sp hybridized, which means they're linear.
Yeah.
And here I'm drawing them like they're bent, right?
Oh, yeah.
And they're not. So it looks more like a needle,
Hmm.
a hypodermic needle. Which makes me think, I've got my vaccines, I'm happy.
Mm.
But that's because I'm old. That's why I was allowed to get my vaccines. I'm old and I'm a teacher.
Oh, I already got my first one.
Excellent.
Yeah, they've been opened up.
So
for
first you
everyone
must
now,
be getting
yeah?
the Pfizer or the Modernas, one of those two, right?
Pfizer.
Is that locally?
Mm-hmm. Here at in Arcata.
Oh, in Arcata. Right, right. I hear that Arcata is the only place in Humboldt to get your shot right now. The open door clinic or something like that.
Possibly, but they have a lot. I'm always getting messages.
Oh, excellent. Yeah, I don't know. My kids were going to get the Johnson and Johnson.
Oh, yeah.
2 days before they went in to get their shot, they got a message saying, "Oh, we're not giving that out anymore."
Yeah, my little sister took that one.
And then now they've okayed it again. But
Yeah.
I think that I would be a little worried if I were a woman because of those
The
women who
blood
are getting blood
and
clots.
stuff. Yeah, especially if they're taking birth control or anything.
Yeah, birth control can cause some women to have strokes because of blood clots. And so I think definitely if you have a history where you've had strokes from birth control, that you really want to be careful about taking the Johnson and Johnson.
Mhm.
But this is a total non-professional, non-medical opinion. It's just kind of, well, you know what? I would just be concerned. And if there's the Pfizer and Pfizer, go out and get that.
Yeah.
All righty then. Good session. I will post this later tonight. Hopefully I'll hear from you guys tomorrow or whenever you need help. And you guys know for the rest of the semester, we're in the end 2 weeks here. You are going to have to take the 4th exam about 2 weeks from today. Today's Tuesday, isn't it?
Yeah.
So normally we would take the 4th exam next week on Thursday. But what I'm done is I'm going to make you take it the following week on Tuesday. So that gives you more time to study for the 4th exam.
Okay.
Also, the final exam we take usually on Thursday of finals week. So that's not going to change. Tonight or tomorrow, I'm going to put out a example lab report. That's the one more big thing that you have to do. And you're going to have to write a lab report between now and your 4th exam. To give you a little bit more time to do that, this week, you're only getting 1 lab, not 2. And next week, you're going to get 0 labs. And that will give you the time to write your lab report.
Okay, so our
Capiche?
last lab is this week.
Pardon me?
Does that mean our last lab is this week?
Yeah, it's that gas lab.
Okay. And the final is on the 13th, 2 days after the 4th exam.
Yes. And luckily for you, since you've already taken the other exams, you should be kind of prepared for 3/4 of the final. And when you study for the 4th exam, that will be the freshest stuff in your memory for the final exam. The final exam is multiple choice.
Yeah.
And it's, I want to say 15% of your grade or 10%, I can't remember which. Okay.
Sorry, my internet dropped like a couple of times while I was in lecture right now. Sorry. Can I ask a question?
Yeah.
So I'm sorry, when are you posting the lab report that we have to write? Today?
Either today or tomorrow. I'm going to give you a sample lab report so that you know what to do for your lab report.
Okay.
And your lab report is going to be on that lab where you tried to find out whether you had sodium carbonate or potassium carbonate or lithium carbonate.
Mm-hmm.
So
you've gone through all of them?
Pardon me?
Have you gone through the labs to figure out if we got it right or not yet?
I'll let you know.
Okay.
So about the same time that I post the sample, I'll let you know if you got it right or not. And you'll have about 2 weeks to write the report.
I guess there'll be plenty to write about if we get it wrong too.
There should be plenty to write about if you get it right too.
Okay.
I struggled with that one in particular, but I mean, at the end, I got some numbers that kind of made sense, but I was able to guess which one it was, but hopefully.
At the end of the day, the discussion might differ in length if you got it wrong. Okay, because in the discussion, I let you know, well, this is what you really had, and you find out that you got it wrong, you're going to say, okay, first thing you're going to do is redo your numbers and see if you get the right answer when you redo your numbers.
Yeah.
And if you do, then your discussion is real easy. You say, well, when I did this step, I screwed up.
Right.
And you tell people how you screwed up. If your data just gives you the wrong answer and you're doing it all correctly, then you need to think about experimentally what happened. And regardless, if your number is not right spot on, you need to give good reasons why it's not spot on and reasons that make sense. So for instance, if the molar mass you got was too big for the substance you got, so let's say one of them was supposed to be 142 and you got 144, which is pretty close. You would say, well, my number's too big because of this. Or let's say you're supposed to get 167 and you got 160, which is still pretty close. You'd say, well, I was kind of close. I was able to identify it, but the reason my number was too low is because of this. So you'd, regardless of whether you got it right or wrong, you would still explain why your numbers were not spot on. And they probably are not spot on.
Yeah, I had to redo mine, and then you didn't give us enough materials to redo our lab multiple times.
Nope, there wasn't.
Right.
There's probably enough material to do it maybe twice if you were careful.
Did. It was I ran out of stuff after the second attempt.
Yep, 2 times. And so that means that actually when you do something and you think you screw up the first time, don't throw everything away. Keep it. Because, it may be that you didn't dry it long enough. And if you kept it for a few days more, it would have dried some more.
Or if maybe
Yeah.
that paper absorbed a bunch of moisture.
Right. Well, and that means you just let it dry longer. And you definitely don't turn the oven up because the paper bursts into flames at a certain temp.
Mhm.
And then you're just messed up. And even from there, there's a way to salvage it. I won't tell you about that.
Hopefully that doesn't happen.
Well, at this point, we can't really redo the lab. So.
There is
Right.
a way to salvage it, but you could also screw it up even more. So, at any rate, so no more labs from here on out, except for the last lab, which was the gas lab, where you're supposed to watch videos.
Mm-hmm.
And that's this week. It's already available. You watch the videos, you do the lab.
That one's due today.
That one was due today.
The galvanized lab is.
Oh, that was due today. What did I put out for this week?
You haven't put anything for this module.
Oh, okay. Well, then you got the lab report. So all you got left for this week and next week is the lab report.
Nice.
And if you can't do that in 9 hours, that's kind of sad.
What's the word count?
Word count, 2,641.
Why so specific?
Because I'm pulling your leg. You should feel like you're getting taller. There is no word count, Rebecca. It's just whatever it is you need to write.
Okay.
One last question, Tony. When
Sure.
are we going to be done with this module, and are you going to continue to have, and until when are you going to keep having lectures? Because in case we have questions
I will be
later on.
available all through finals week, except for I'm not going to be available Thursday.
Mm-hmm.
So the day of final, I'm not going to have any lectures
Until Wednesday
or
then?
any Q&A, but I will have Q&As up and through to that Wednesday before the final. And I think the final is on the 15th.
Mhm.
I think.
13th is, I think the 14th is a Friday, so the 13th is a Thursday.
Okay, so the 11th is exam 4 and the 13th is the final.
On the Thursday, the 13th.
Okay, and Tuesday is exam 4.
Yeah, the 11th.
That's the 11th. So I will be doing these sessions all the way up until the 12th.
And we'll be done with chapter 23 next week or this week?
Well, this week you have this week and next week to work on chapter 23.
Okay.
I mean,
And
but
technically you could still be working on chapter 10 or whatever.
Okay.
You could be studying for the final.
Right.
So with 2 weeks, that should be enough to learn the materials in chapter 23, write your report, prepare for the exam 4 and for the final,
Okay.
especially since you guys don't have any more labs to work on.
Mm-hmm.
All right.
Okay.
Thank you, Tony.
You bet.
Awesome.
We will talk to you again.
Have a good night, guys.
All right.
All
Good
right. And
night.
remember, Rebecca, Emily,
Oh, Emily Wright. Is
correct.
that last name?
Yeah, and she and her husband do a lot of climbing around Humboldt County, and they even go other places too. They're avid rock climbers,
They sound cool.
and I think
Have you been doing that for a long time, Rebecca?
I've been rock climbing since, I guess, a while, since before 2010.
That's a good decade.
Yeah, I mean, I was doing it. It's more recreational, though. You know, I'm not. Yeah.
So, what are you up to? Are you like doing 5'10s, 5'11s?
Yeah, I do like I do 5'10s and project 5'11s, but I like bouldering more. I think we talked about this last time.
So
I'm
is-
doing like, I project like V4s and V5s.
So Issa, here's the deal. I do
It's
like
pretty
five.
good.
I do 5 2s and 5 3s. And a 5 3 means that you can basically
Those even exist in a gym or outside at all? Are all jugs?
a 5 3 is basically you can walk up it without the use of hands.
Yeah, I know. I've been to I used to go to Sender One climbing gym in Santa Ana in SoCal, but I was not that good at all. Not nearly close to where Rebecca's at.
Well,
I was
it
gonna say I'll go with you, Rebecca, and then I was like, never mind. You seem pretty advanced.
Yeah,
It
if
takes
she's
a lot of time though, and I've plateaued, you know, I'm too short, I think.
if she's getting into the double digits, 5, 10, and then the letters, you know that she's pretty serious.
I know.
I mean, she's even doing letters. It's like, oh my
I've seen
God.
people rock climbing at Moonstone Beach. There's some kind of
yeah.
a wall there.
There is. It's
Oh, you
nice
mean the
there.
rock? You mean that rock in the middle of the beach?
Yeah. I've
You
seen
go
people
that's
climb it.
left or you go right, and it's on your right about halfway through to the back cave back there.
Oh, that's different. There's also a rock kind of in the middle of the beach, kind of right there.
Oh, I know what you're talking about too. I think when the
Yeah,
tide's low,
that's-
people do that.
That's like a 5 2.5.
Okay. Right.
I used to do that one all the time. That one used to be easy for me. Now it would be impossible. All right. Nice talking with y'all. Hope to hear from you soon. You probably want to call in more often than not for this particular chapter because it's unlike any of our other chapters. It's very descriptive in many senses and not calculations.
Yeah.
All right. You have a good evening.
All right. Bye, Tony.
Bye-bye.
Bye, Rebecca. Bye.
Bye.